Why do atomic nuclei manage to resist the tremendous repulsive forces without falling apart? Why can white dwarfs resist their own gravity? But when they exceed a certain mass, they collapse instantly into neutron stars. And why, when you keep pressing a neutron star, does it inevitably become a black hole? In the energy filament theory, these seemingly completely different celestial bodies are actually variations of the same principle, different levels of balanced structures within the energy sea. Who takes the lead in this pressure battle depends entirely on how much tension you apply. Let's start at the smallest scale, the atomic nucleus. Protons, being positively charged, naturally repel each other, trying to push apart. However, the strong interaction, completely different from electromagnetic forces, has a strict rule: gaps must be filled. The quarks and the protons lock together into nucleons, and these nucleons are further bound by short-range binding patterns that close the color lines. At this scale, the strong interactions locking mechanism is powerful enough to resist Coulomb repulsion, electrostatic force, and quantum fluctuations. The atomic nucleus becomes the first tension balancing unit in the energy sea. When many nucleons come together to form a star, at first, the star could resist gravitational collapse with thermal pressure and the energy released through nuclear fusion. But when the fuel runs out and thermal pressure can no longer support it, gravity takes over, further steepening the tension slope. This is where the next level of balance comes into play, the white dwarf. Here, electrons are compressed into smaller spaces, a phenomenon known as electron degeneracy pressure. In terms of energy filament theory, this is not merely compression. It's because many of the electron orbitals are already filled, and further compression forces electrons to occupy higher, less stable orbitals. This forces the energy sea to pay a high price, resulting in the material showing strong resistance to compression. This explains why white dwarfs can temporarily withstand gravity. They push back against immense pressure. However, when the mass of the white dwarf exceeds a certain limit, the tension slope becomes steeper, and the balance within the electron layer is pushed beyond its breaking point. Some of the electrons can no longer stay in their outer orbitals. Instead, they are forced back into the nucleus, merging with protons to form neutrons. The electron orbital structure is dismantled, and the next level of balance begins: neutrons and the strong forces. The star's structure transitions into a neutron-dense arrangement, where the neutron circulation and strong nuclear forces balance out the gravitational pull. This stage is called a neutron star, which is much denser and more resistant to collapse than a white dwarf. However, the neutron star remains a finite arrangement within the energy sea, and its tension balance is still constrained. Now, if you continue adding mass to the neutron star, even this dense neutron structure reaches its limit. The strong interactions rule of map filling has nowhere else to go. It has exhausted all possible neutron arrangements. Gravity, now fully dominant, begins to overwhelm the neutron structure. The energy sea no longer tries to find balance in the local structure. Instead, it collapses inward, forming a unified macro tension slope. This state is referred to as the full takeover, resulting in the formation of a black hole. So, when we consider the progression from atomic nuclei to white dwarfs, to neutron stars, and ultimately to black holes, these are not four separate, unconnected phenomena. They are all stages in the life cycle of the same energy sea, each one activated under different pressures, gradually transitioning from one form of balance to another as tension increases. First, the strong force locks quarks and nucleons together at the atomic scale. Then, electron orbitals hold the structure against further collapse. And when they could no longer resist, neutrons and the strong forces took over. Finally, when neutron configurations are exhausted, gravity prevails, and the entire energy sea collapses into a pure gravitational tension slope. All that remains is to follow this slope to the black hole at the end of the journey. In essence, the formation of stars and their transition into white dwarfs, neutron stars, and black holes is not a collection of unrelated bodies. They represent different configurations of the same underlying energy sea, activated at different stages of pressure. From atomic nuclei to white dwarfs, to neutron stars and black holes, they are merely successive balancing structures in the energy sea responding to the forces of tension at different scales. This dynamic shows us how celestial bodies form, evolved, and ultimately succumbed to the forces of gravity and tension, as they follow the path of least resistance down the tension slope to the ultimate state of a black hole. Tap follow, share it on New Physics, Clear Universe.